Good morning, everyone. My name is Sharon, and I am from CSM AIML Section C. So, today my topic is applications of graph theory in computer science. So, let us start the topic. Applications of graph theory in computer science. A presentation exploring the fundamental role and diverse applications of graph theory in solving complex computational challenges across various domains. It is a presentation that explores the fundamental rules and also explores the applications of graph theory in solving complex domains. So, what is graph theory? A quick refresher. Graph theory is the study of relationships between objects. These relationships are modulated using a mathematical structure called a graph, which consists of nodes. Nodes are vertices, the fundamental entities or objects being connected. Example, cities, users, data points, and edges. Edges, the links or connections between the nodes representing the relationships. Example, roads, friendships, dependencies. This abstract framework provides a powerful tool for visualizing and solving problems involving connecting systems. Graphical representations. Agency matrices versus agency lists. In computer science, graphics must be stored efficiently for algorithm processing. The two most common methods offer different trade-offs in terms of space complexity and time complexity. For common operations, adjacent matrix, a 2D array where the entry at row I and column j is 1 if there is an edge between node I and node j and O otherwise. Pros, quick lookup for checking if an edge exists. Cons, high space complexity, inefficient for space graphs. And coming to adjacent list, an array or hash map where each index node points to a list of its neighboring nodes. Its pros, efficient for space graphs, less memory required. And cons, checking for edge existence taking. And the shortest path algorithms, Diksha's and A for navigation and routing. Longest path algorithms are central to many applications, determining the most efficient route between 2 points on a weighted graph. GPS navigation, finding the quickest route between two locations considering traffic and distance. Network routing, optimizing the path of data packets across the internet or a local network to minimize latency. Gaming AI, enabling characters to navigate complex environment efficiently towards a target. And network flow problems, optimizing supply chains and data transmission. Network flow models treat edges as pipes with capacities where the goal is to maximize the flow of material from a source to a sink without exceeding any capacity. Supply chain logistics determine the maximum amount of goods that can be shipped through a distribution network constrained. And telecommunications maximizing the amount of data that can be transferred between routes in a communication network, identifying. And traffic management, graph coloring, resource allocation and scheduling challenges. Graph coloring involves assigning colors to vertices such that no adjacent vertices share the same color. The minimum number of colors needed is the chromatic number, and this translates directly into research optimization problems, timetabling and scheduling, assigning classes to time slots such that no student or teacher is double booked. That is, conflicting classes cannot share the same time slot. Second one is register allocation in compilers, allocating variables to processor registrations, ensuring that variables that are alive at the same time are assigned to different registers to avoid conflicts. Coming to third point, frequency assignment. Assigning radio frequencies to transmitters in a circular network prevent interference between adjacent cells. So these 3 points use graph coloring. And social networks, analyzing connections and influence. Social media platforms are massive graphs where users are nodes and interactions, friendship follows, are edges. Graph theory is essential for understanding the structure and dynamical uh, digital communications. So here you can see a diagram that's representing key influencing and social networks. So the first one is community detection, that is identifying clusters of tightly connected users. And the second one is centrality measurements, rank influential nodes by connectivity and research. And the fourth one is link prediction, forecast linkly future connection between users. And the last one is information, that provides the information and a model through the network. This is how social networks uses the graphs. Machine learning with graphs. Graph neutral explained. So here, traditional machine learning suggestions struggles with non-data like graphs, graph neutral networks, GANs. We call GNNs as graph neutral networks are a revolution, extending deep learning to a natively processed graph structure. And the key concept is message passing. GNNs work by iteratively aggregating and transforming information messages from a node's neighbors, if effectively learning a rich presentation for each node based on its local neighborhood and applications. And it is used in drug discovery, modular research, recommendation engines, and traffic forecasting by considering spatial and temporal distances. Security and cryptography, graph-based attacks and defenses. So graph is also used in attacks and defenses that are used in security. So graph theory provides models for both protecting systems and identifying vulnerabilities, especially in complex interconnected infrastructures. So let us look at this. Vulnerability analysis, modeling a system's assets and dependencies as a graph to identify critical paths for potential exploits. Attack graph and fraud detection, identifying suspicious transaction patterns or money laundering rights by detecting complex substructures and anomalies in financial transaction graphs. And post quantum crypto, lattice based cryptography, a candidate for post quantum security, often relies on mathematical structures that can be related to graph problems. The future, emerging applications and research directions. The utility of graph theory continues to expand as system becomes more interconnected and data becomes more complex. Quantum computing. So graph theory is also used in quantum computing, bioinformatics, and digital twins and IoT. So let us look at quantum computing. Solving massive graph problems such as Hamilton path or maximum click, which are correctly interactive for classical computers. And bioinformatics, detailed analysis of protein to protein interaction networks and complex genetic regularity pathways. And digital twins and IoT, real-time modeling and quantization of large-scale smart city infrastructures. Graph theory remains a provisional framework for addressing the most suffocating challenges in modern circumstances. And from all this graph theory, we have learned that a vertex node is a fundamental unit that can represent a person, and the basic is vertex and edge. Edge is a connection between two vertices, and also we have learned that where we will be using the graph theory in the modern era, and we got to know about graph theory in usage in computer application and computer science. And thank you.